Greetings all. The material that we're covering today is partly review from first year chemistry, but partly some rather complicated stuff. Some of you might find that you do just fine, reading the chapter by yourself and reflecting on it. Others might find my comments on the remaining part of the chapter very helpful. Do what is best for your learning and for your time. As we talk about the solubility and the common ion effect, remember that common ion does not mean an ordinary or abundant ion. It means an ion that is in common between two compounds. For example, if I had silver acetate and silver chloride, the silver ion would be in common between those two compounds. Now, the ionization of weak acids and bases, that means the ability of weak acids and bases and salts to separate and dissociate in water, is affected by the presence of an ion common to the equilibrium process. In other words, if I add a common ion to an equilibrium that is already established, it will drive the equilibrium to the left, according to Le Chatelier's principle. But in going to the left and creating more precipitate at the bottom of the beaker or test tube, it will also reduce the molarity of the other ion, the one that is not in common. And that, of course, can be very helpful if that other ion is an ion that we don't want to be in solution. For example, if we don't want to dump it down the drain because it would be dangerous. Let's take a look at problem example 18.11. We have some solid silver chloride. We put it in 1 liter of salt water. The concentration of that sodium chloride is 0.55 molar. The question says, determine the solubility of silver chloride in the presence of excess chloride. The steps are what we've talked about before. Always write the balanced equation, showing the equilibrium and showing the dissociation of the insoluble or weakly soluble salt into its ions. You can see that a little bit farther down at the very top of the ice chart. Secondly, you're always going to write the equilibrium expression. The equilibrium expression is always the products from the equation multiplied together, divided by the reactants from the equation. Of course, since our reactant in this case is a solid, it doesn't show up in the expression. And you can see the KSP expression towards the bottom of this page right now. Then we set up our ice chart in order to figure out the data that eventually we're going to plug into the equilibrium expression. And then step 4 is where we pull out the calculator and do the math. Now, you'll notice that in the ice chart, the initial molarity of silver ions is considered to be 0. One way to look at this is to imagine that we've put the silver chloride into the water, or we are about to, and there's no silver in the beaker at all. Another way to look at it is even if we've put the silver chloride into the beaker of salt water, the molarity of the silver ions that have dissolved is very, very, very small. And at least to 2 significant digits, it would round off to 0. Meanwhile, the molarity of the chloride ions is given to us in the problem and is 0.55 molar. because sodium chloride is very, very soluble. So you're going to have 0.55 molar sodium ions and 0.55 molar chloride ions, because every sodium chloride will dissociate. Every square dance couple will split up. The sodium ions are, of course, spectators. Then, because the reaction has to go to the right, because there's no silver ions to speak of in the solution when we add the silver chloride, that means we're going to increase by some amount X both the silver ions and the chloride ions. This is the stoichiometry step. The change is 1-to-1 because every silver chloride that does manage to split apart will produce the same number of silver ions as chloride ions. Finally, in the E, or equilibrium, part of the ice chart, we add the first two columns together, or first two rows together, and we get X for the silver ions and 0.55 molar plus X for the chloride ions. Now we plug those numbers into our equilibrium expression, our KSB expression, and like before, we ask ourselves the question, can we ignore the plus X? Is X going to be so small that when you add or subtract it from the other number and round off to two significant digits, which is what we're pretty much limited to in these kinds of problems, will it show up or not? Will it make a difference or not? And of course, your KSB is 10 to the minus 10th. And if you multiply that by 100, which is our standard, 2 zeros in 100, two significant digits, you get 10 to the minus 8th. And 10 to the minus 8th is still way, way, way smaller than 0.55. So we can ignore the plus X, which simplifies the math. Now we just punch these numbers into our calculator and hopefully do so correctly. And we get the molarity of our silver ions as 3.3 10 billionth molar. And we can convert that into grams per liter by using the molar mass of silver. Here's another problem on page 836. In this case, we want to calculate the solubility of silver chromate. It may have been a while since you've used the chromate ion. Remember, it's a -2 charge. And make sure you remember that silver is a +1 ion, because silver ions are very common in discussions of chemical aqueous equilibria involving relatively insoluble salts. Notice that we also have another chromate solution, potassium chromate. When we write our equation, we always write the equation for the insoluble salt, not the soluble one. That means we write the dissociation of silver chromate, not potassium chromate. Because silver chromate will reach equilibrium, the potassium chromate, unless it were to be super concentrated, will not. Then we're going to write the equilibrium expression, products over reactants. The reactant is solid, so our denominator ends up being 1. Don't forget, it's a 2-to-1 ratio, so the silver molarity must be squared. And notice that the KSB is quite small, 9 trillionth. Now when we go to do our ice chart, again, the amount of silver ions, either before we add the silver chromate, of course, would be 0, and even after we add the silver chromate would be negligible from the silver chromate. But the chromate ions are pretty much exclusively all from the very soluble potassium chromate. whatever chromate ions there might be from the silver chromate would not even show up if you were to add them to that number. Now, when we do the stoichiometry, we have a 2-to-1 ratio of silver to chromate. Therefore, as the reaction goes to the right, every silver chromate is going to produce 2 silver ions for every 1 chromate ion. Finally, we add those 2 rows together and again ask ourselves the question, can we ignore the plus X to the 0.0050 molar chromate molarity? And most assuredly we can, because the KSP is so incredibly small. That simplifies the math. Here's a most common mistake. Notice that we have 2x, and it looks like I'm getting an email from the Wall Street Journal. Notice that we have 2x that has to be squared, and 2x squared, where you have parentheses around the 2x, is not going to give you the same value as 2 times x squared. Make sure you do your algebra correctly. 2x quantity squared gives you 4x squared. And of course, notice that the solubility of a salt will be reduced by the presence of a common ion, and we're using Le Chatelier's principle. Now we get into a topic that is a little bit more technical and builds on what you had before. The effect of basic anions on salt solubility. So what is a basic anion? It's going to be an anion that, when it hydrolyzes, produces a basic solution, produces hydroxides, if you want to think about the Arrhenius definition, or receives a proton, if you want to use the Bronsted-Lowry definition. And salt solubility is simply meaning how soluble is that salt. Can we make an insoluble salt, at least in water, become more soluble? And I highlighted in blue an important phrase. The solubility in water may be greater than you think, in part owing to the possibility that the anion of the salt is a weak base, or the cation is a weak acid. So anions can act as weak bases, cations can act as weak acids. And so things that you might think are safe to dump in the water because they're going to precipitate out might actually not precipitate out and stay in solution, which of course would be dangerous if people were to try to use this water for whatever reason. So consider lead 2 sulfide. Pretty insoluble, dissociates into lead ions and sulfide ions, making an equilibrium situation. But that sulfide ion happens to hydrolyze quite readily, as you can see in the second equation. And when it hydrolyzes with water, it produces the hydrogen sulfide ion and a hydroxide ion. Again, it's helpful to think about water as being hydrogen hydroxide and donating its proton to the sulfide ion, creating the bisulfide or the hydrogen sulfide -1 ion, leaving behind the hydroxide, which means it's acting like a base because it produced a hydroxide. Notice that the equilibrium constant here, the Kb for this base, is 10 to the 5th, or 100,000. So this most definitely goes to the right. So using Le Chatelier's principle then, if the sulfides continue to hydrolyze, What you are doing, in a sense, is removing the sulfides from the equilibrium reaction of lead sulfide dissociating into lead and sulfide ions. And as those sulfide ions are being removed, the lead sulfide continues to go to the right, thereby increasing the concentration of lead ions in water. And of course, as we know from Flint, Michigan, that is not a good thing. Or, as you've heard before, you hate it when that happens. Couple of other comments. In the blue boxes, any salt containing an anion, that is the conjugate base of a weak acid, will dissolve in water to a greater extent than given by the KSB. And that's what we just talked about. Now, the generic form of an anion hydrolyzing is represented by the X minus, where X is your generic anion, and you're going to produce a hydroxide. But X is going to be the conjugate base of the weak acid. That is to say, what's left over when the weak acid donates its proton. So insoluble salts in which the anion is the conjugate base of a weak acid will dissolve in strong acids. And now you're getting the idea that in first-year chemistry, we pretty much made a distinction between dissolving in water and chemically reacting in water. When we start talking about these anions and cations hydrolyzing, it kind of blurs that distinction a little bit between dissolving, which is a physical process, and reacting, which is a chemical change. So sometimes we talk about dissolving acids and bases in water as being a reaction. Now, the discussion in the bottom part of this page in first-year chemistry was simply calcium carbonate, when it reacts with water, will produce a salt and carbonic acid, and carbonic acid will dissociate further into water and carbon dioxide. So if we cancel out the spectator ion here, which might be chloride or nitrate or something like that, you can see that this reaction goes to the right because not only are you making a molecule with a strong bond like water, you're also making gas, which would leave the equilibrium environment. But let's look at it a little bit more carefully. Here you have 4 equations in a row, beginning with calcium carbonate right there, and calcium carbonate dissociating into calcium ions and carbonate ions doesn't happen readily. Notice that its KSB is 3.4 billionth. However, that carbonate ion, like we said before, will hydrolyze, creating the bicarbonate ion right there. And then that bicarbonate ion in the next step can further hydrolyze to make carbonic acid right here. And when you look at their equilibrium constants, and when you look these up, they're in the chart in the reverse, so you've got to take the reciprocal of the Ka. You'll notice that these equilibrium constants are quite high. 2.1 times 10 to the 10th, or we could say 21 billion, and then the other one is 2.4 million. When we put all 3 of these steps together, we have to multiply those K values to get the overall or net K value, and you can see it's quite high, 1.7 times 10 to the 8th. In other words, we've made the solubility of carbonic acid very, very, very likely. We've gone from a billionth all the way up to 100,000. The very bottom of the page says many sulfides are also soluble in strong acids. And now they use the example of iron sulfide in a strong acid. And of course, when we talk about a strong acid, that means that the cation in the strong acid, the anion in the strong acid, like chloride, nitrate, sulfate, is a spectator ion, and we don't write it in the equation. Phosphates, metal phosphates, also hydrolyze or will react in water, and you have the hydrolysis that goes on with those ions to increase their solubility. And so we can conclude that in general, the solubility of a salt containing the conjugate base of a weak acid is increased by the addition of a stronger acid to the solution. Now, if you feel like you need practice doing these review and check for understanding sections are always very helpful. Some of you will benefit from thinking through this carefully, and others might have picked this up pretty well and you don't need to do this. Precipitation reactions, or reactions that make a precipitate. This is really practical because, as you can see, these metals aren't just lying around on the top of the earth and we just go pick them up. All the resources that we need on our planet primarily come from mining or growing. We can extract a little bit of stuff from the atmosphere and sometimes from ocean water. But pretty much everything that we run our civilization on either has to be mined or grown. And of course, the miners and the farmers are the people that begin this entire process. And between you and me, I do not think they get enough credit or enough respect from other people for the work that they do, which is sometimes very, very dangerous. Metal-bearing ores, then, an ore, O-R-E, is going to be a compound that contains the metal. Only a few metals are you going to find not combined to make an ore, which is why people like to mine for gold or silver, because these metals, being relatively inert, means you don't have to do much chemistry in order to get the metal. The other metals you really do have to do a lot of chemistry. And the other thing that we need to point out is that when we mine these ores, the very volcanic processes that often concentrate one metal will similarly concentrate other metals in the same vein or portion of the strata. Therefore, not only do you have to get the ores out of the ground, but then you've got to separate the metal ores from each other, and then you've got to separate the metal from the ore. So it can be a complicated process. It's one of the reasons why it's always good to recycle these metals. And one of the ways that we get these metals out is by using what we call a precipitating agent, something that will help to precipitate the metal ion out as an insoluble salt. For example, if you look at these two equations, if we have a nickel-bearing ore, nickel Roman numeral 2 ions, and we add a compound, for example, that contains hydrogen sulfide in it, we can precipitate the nickel out as nickel sulfide. And in this process, we might be able then to separate nickel sulfide from nickel carbonate if we happen to have a mixture of these two nickel ores in the same chunk of rock. How do we then separate the metal from the rest of the ore? We would do that either chemically or electrochemically which will be the focus in chapter 20. Now, here you might remember some things from last year, the reaction quotient. In the reaction quotient, represented here by the letter Q, Q is the result of dividing. That's what the word quotient means. Divide the numerator by the denominator. Of course, with KSBs, our denominator is 1. But we still use the letter Q because we can have a reaction quotient with weak acids and weak bases, as well as weakly soluble salts. When we are given a problem and we have concentrations of cations from one compound and concentration of anions from another compound, and we mix them together, it would be very unusual if the molarities of the cations and ions in solution, when we multiply them together, just happen to be exactly the KSB. That would be kind of contrived. So since we don't know whether this is going to be at equilibrium or not, we just call this letter Q, and then we're going to compare the value of Q to the value of K. And if Q happens to equal K, then we know we're smack dab at saturation. But if Q is less than K, then we know the reaction is not yet saturated, and we can add more salt, and the reaction can continue to go to the right until it reaches equilibrium. On the other hand, if Q is greater than K, that means that this reaction has exceeded the equilibrium, and therefore we would expect there to be an awful lot of precipitation and stuff sitting at the bottom of the test tube or beaker. Hopefully you remember that from last year. Now this excursion or excursus about the oceans is very interesting. It probably needs some updating because one of the big mysteries in the carbon cycle and in the discussion of carbon in its role in climate is just how well and how much does the ocean concentrate carbon. Certainly the oceans in the atmospheres are sort of a large example of what's in the beaker, and you have an equilibrium going back and forth between the carbon dioxide in the atmosphere, the carbon dioxide dissolved in ocean water, and the carbon dioxide that might be in equilibrium with carbon-containing compounds, especially carbonates, represented by, for example, all of the shells and skeletons of many organisms that live in the oceans, not to mention lots of the rock materials and corals that might be in the bottom of the oceans. Very, very, very complicated chemistry. And between you and me, I would say that this is a marvelous example of a very significant balance and design that enables human beings to go about the business of flourishing and building cultures. And when we do this in a God-honoring way involving stewardship, the oceans and the atmospheres are established in such a way that they can tolerate the kinds of changes that might occur in the oceans and in the atmospheres. But we're going to see a bit of a negative result or pushback when we go about the business of human activity and we don't do this in a way that is careful and considers its effect on God's creation. And so here's an excellent example of where biblical stewardship is always the right approach as we do our industry and develop our technologies and go about the business of human flourishing on the planet. We also want to consider the rest of God's creation. He's designed it in a way to enable us to do what he wants us to do, to fill the earth, to be fruitful, to multiply, to have dominion in a God-honoring way, but it's going to push back when we don't do it in the right way. Let's look at this next example where we have some solid silver chloride in a beaker of water. The same sequence of steps. Write the equilibrium equation, silver chloride dissociating into silver and chloride ions. Write the Q expression, or the equilibrium expression, I should say, of products over reactants, the KSP. Then we plug in our numbers. Notice that the molarity of the silver ions comes from one source. Let's say it's silver nitrate, and let's say the chloride ions comes from sodium chloride. We ignore the spectator ions, and the amount of silver and chloride ions that might come from silver chloride is insignificant compared to the molarity of silver and chloride from the original salts. Once we do the math, we can compare the Q value from the calculation with the KSP and draw our conclusions. This enables us to decide whether or not a precipitate will form. And not only that, we can also calculate what is the concentration of the ions in the solution when we reach equilibrium. And that's what this next problem does, that's embedded in the text with magnesium hydroxide. Now, what's different about this problem is magnesium and hydroxide are in a 1:2 ratio. So you've got to remember the stoichiometry. So, and I'm looking right here, it's not highlighting at the moment, but the magnesium hydroxide dissociates into a 1:2 ratio. We plug in our math from the magnesium source, and we plug in the value for the hydroxide source, and notice, and this is a common point of misunderstanding, the hydroxide molarity is not twice the magnesium molarity, because the hydroxide molarity did not come from magnesium hydroxide. It came from some other source. And the magnesium molarity did not come from magnesium hydroxide, but from some other source. So the stoichiometry doesn't show up here. However, it is squared. The hydroxide molarity is squared because that's required by definition of the KSP expression. And you can do this example again with barium sulfate in this part of the problem. This is pretty straightforward. And again, you did this in first-year chemistry. The barium and the sulfate ions come from two other compounds, and you plug them in. They did not come from taking some barium sulfate and dissolving them in water. This is an example of a precipitation reaction. Example 18.15, calculate the amount or moles of each substance. Remember I said that any time you're given both the volume and the molarity, you're going to multiply the two together. So down at the bottom, we multiply the volume times the molarity to get our moles of barium and our moles of sulfate. Then we divide by the new volume. That is what people forget. You're adding two solutions together, so you have to add the two volumes together to calculate your new molarity. Once you calculate the new molarity, then you can plug these values into your equilibrium expression and compare the value of Q to K. This was actually very close to a problem that you had on a test in first year chemistry. I'm going to stop here and we will finish the chapter later.